numerical simulation, and the previous talk, the title is gas solid flow, but I changed it a little bit to particle fluid flow because I also talk a little bit about the simulation of a stirred tank. So first some background. And so actually there are many ways to do direct numerical simulation, and basically I think there are two numerical methods, discrete and continuum based. And actually for discrete methods there are some prototype ones like molecular dynamics and DEM. And actually we can do a lot of tricks to either do some stochastic process or coarse graining or simplify their interactions, and then we can develop some more methods like DSMC, DPD, and lattice Boltzmann. And on the other hand, for the continuum methods, both for the solids and for the fluid flow, we have this finite difference or finite volume or the finite element method. And actually, in terms of the algorithm, you can still use many different ways to reduce into particle-based, lattice-based, or stanchial-based, or matrix or mesh-based methods. So I find maybe we can still find some part are the Lagrangian-based, some part are Eulerian-based, and in some sense they are discrete methods, and some sense they are continuum methods. So actually, I think the difference between continuum and discrete methods are not so obvious if we go down to the algorithm side. So, and then more complicated is each phase can be simulated with different methods. So in principle, we can have this two-dimensional matrix, and every cross-sectional cell should present a kind of simulation method. But we can see that at the moment we still have very few choices. So there's a vast space for future development. But in terms of the operating methods in particle fluid flow, I think in the stream we have the most detailed direct numerical simulation method, mainly based on the particle DM method and the fluid flow solved by the Navier-Stokes equation at the particle resolved level. And on the other hand, the two fluid model, both solid and fluid, are treated as continuum. And in the industrial applications, we actually now are almost at this stage that, for example, in fluidization, a lot of people are now using MPPIC method for the simulation. But I think maybe with the help of stable computing on one side, and on the other side, so-called mesoscale modeling or subgrid scale modeling, we can someday move this pointer to this area. We call it coarse-grained particle method. So we still have the fluid flow solved at a scale larger than the particles, but the particles can be tracked as collections of many particles, and then it can go to the real commercial scale. But with this, we need a lot of information from the DNS level to provide the constitutive laws. So I think this DNS maybe is important because of this mesoscale scaling modeling need. So then to the DNS method we are using now, we actually mainly using two varieties. One is the gas phase is based on LBM because it's a very fast and explicit method, and the solid phase is on DEM. And both the gas phase and the solid phase can make use of GPU computing for scaling up. For go to larger scales, And, but this is not always working because if we try to have higher stability and we try to cooperate reaction and transport processes, and then LBM sometimes are not so convenient. So we also develop some methods using the traditional finite difference method. And this is not easily parallelized like LBM. But somehow we can still make use of the GPUs to some extent. And so there are, and for the coupling, we are using the IBM method because it's relatively lower cost and it can treat complex geometries very easily. So these are the main methods we are using now. What is problem? It's not moving forward. It's not moving now. Okay. Uh-huh. Huh? Sorry. Yeah, it's moving?
Yeah.
Okay. So for LBM, we are actually, because we are more interested in a large-scale simulation, so we have to compromise to use the most simple ones. So we are using the bouncing back boundary condition and the most, and also I think the most popular LBGK model with the D3Q19 scheme. And so this is the very typical method. And for FD method, we are using the second order spatial discretization and the third order Runge-Kutta time discretization. And the pressure Poisson linear problem is solved using this hybrid library. So, and the DM part is still using the very classical one from Kandau. So basically the normal the normal force and the tangential force all in quite a linear and explicit method. So with all this, we still need the coupling between the two phases. So in this case, we use the immersed boundary method. So we are using the classical force-induced method. So the force acting on the particles and the torque on the particles are all solved for each surface lattices. And the source term is added to the momentum equation in the fluid flow. So these are the then. How we can organize this computation in a more efficient way. So we analyzed that actually in this simulation we have three kinds of operations. One is for the global iteration and control and communication. And this is more complicated, but it still have very few computation. And then is the collision detection and processing for the DM part. And at the bottom is the cellular automata type calculation of LBM. And this takes a lot of computational power. So in this case, we try to use different processors for different computations. So CPU is for this overall communication and control. And the Intel Mac, so-called integrated many core, is used for the DM part, and GPUs are for the LBM part. So in this way, we can keep a good consistency between the simulated system, the model, and the software and the hardware. So, and so for this purpose, we also developed our own computational node using both three processors in one node. So they are connected by PCIe, and you have the infinite band connections between the nodes. And the actual data, the data are also transferred between these three kinds of processors. And so for example, the FDM calculation, we need to implement also the interaction between this particle and the fluid in this mode. And as I mentioned, we have used the very traditional method. And so this is some performance test in this GPUs. So in the process, we actually have experienced the different types of GPUs. So the recent ones we tried is the K40 from NVIDIA and also P100. So you can see with P100, we can have the best performance much higher than K40 in the single GPU side. But when you use GPUs, the performance upgrade is not so obvious. And this is mostly because the LBM is at last memory and communication bounded computation. So actually these GPUs are too fast for our network. So this may be the problem, and we still need further overlapping between the communication and the computation to speed up this performance. And there's another method we can get higher performance is usually we have 1 MPI data transfer in each LBM step. But in fact, we can, if we can afford to lose a little bit accuracy, then we can do it every 2 or 3, 4 times. Then you can see the increase in the performance. But we experimented maybe only 2 or 3 is most reasonable. And in terms of the performance of the DM on GPUs, it can be very encouraging. So when we use the K40 GPUs, and for a single GPU, actually it is 2 GPUs are combined as 1 K80 GPU in the NVIDIA GPU board. So for these 2 GPUs, you can almost reach 100 million particle updates per second for a single GPU if you are using a simple interaction law. But if you are using a more normal interaction law, then the performance will be almost half. But it is still very significant because you can imagine we can simulate about 10,000 particles in real time using very fine time steps. And also, when these two things are coupled, the LBM is coupled with DM, we can still have good performance when we have very large domains, like this lattice is 128 cubic plus 2. So in this case, we can reach about 15% of the peak performance of a processor. But the number of the flops is counted using our manual counting of the source code. So maybe in the compiler, they will have different number for the real performance. But anyway, I think this LBM is almost at its best performance because it is more or less memory bounded. And then with this method, we can set up some large-scale simulations. So in our simulation, we mostly use the so-called periodical boundary conditions in every direction. But the flow field is driven by a force, the body force in different directions. So the particles are going down and the fluid flow is driven upward. And the overall force balance is to keep the overall momentum is to 0. And at the beginning, the particles are uniformly distributed, and the gas velocity is 0. And then you drive this system to reach the steady state. So this is kind of simulation we can do. And we have, so far, the largest scale three-dimensional simulation using more than 100,000 particles. And the particle-based Reynolds number is about, varies between several to 10 or at most 20. And the actual size, if we map to the gas solid air solid system, is like 70 micron particles, and that's typical for the catalytic fluid catalytic process. And so in the fluidization, still the group A particles. And we also do a simulation for the stirred tank, and in this case, we are using 1 millimeter particles for the water tank with 32 millimeter diameter, and the impeller-based Reynolds number can reach several thousands, and we also tried different densities and different volume fractions from point real 5 to 10. And then we need to sample the results. So in this case, we are using this sampling box, which are moving across the whole domain. So in this case, you can make a full use of every particle data, and we can accumulate a lot of samples for these quantities, like the velocities and their fluctuations. And then we need to understand its local behavior. So in this case, there's some ambiguity in how to define the local properties. So in this case, we are using the Voronoi tessellation method. So we can think about that each particle with its Voronoi volume is its local area. So the fluid flow velocity and also the voidage, everything can be calculated based on this concept. And then if you try to understand the cell-based values, then you can take the average of this each particle. So, so in this case, the particles are again the element for the averaging. So, and then for the stirred tank, because it's not a cubic domain, so we need to do some cylindrical partition, and then to get its average in these cylindrical areas. And this cylindrical area is also based on the particle-based properties, and this particle-based properties is again averaged from the Cartesian grade, which is even smaller. So there's a two-step averaging in this sampling process. So let's see some results from these simulations. And so first is some basic features like the local concentration distribution. So actually, although we find that this gas-solid flow have a very obvious heterogeneity, but if you try to understand its distribution of concentration, it's quite a continuous one. But if we use these two functions to describe the dense and the dilute phase separately, then we can see two functions can give a very close presentation of this continuous distribution. So that means this there is indeed two most probable densities. So this one and this one, which is the visual impression of our naked eyes. So we still don't know how to explain this this phenomena. So then you can understand its fluctuation in the velocities. So there's obvious anisotropic behavior. So these different granular temperatures in different directions are quite different, and also their fluctuations are different. So our sampling is start from the steady state. So you can see at first this granular temperature is increased, but and then it is fluctuating. And we start with a stable fluctuating period. And then in terms of its magnitude, you can see it's different from the same temperature Maxwellian distribution. We try to use different temperatures to fit this, but anyway, you cannot fit it in the Maxwellian way. So then we go to other properties like the forces. See that the force is the overall drag is in balance with the gravity very quickly. Although there is a fluctuating behavior, but the overall average is very stable. But then if you calculate the local Reynolds number, and its fluctuating is much higher. So that means the structure is changing, but this changing structure can always balance the gravity. So in this sense, this system is in a steady state, but still there's a lot of structural changes. And you can see the forces are also very anisotropic. So this X value is widespread and it is higher. So the interesting thing is the most probable force in the gravity direction is not in balance with the gravity itself. It's a little bit smaller. So that means most particles are in fact are in deaccelerating, and some are in accelerating but at a very high acceleration rate. So overall there is a balance. And we also noticed that there is a very strong scale dependence in terms of the slip velocity. So if we simulate this rectangular domain with the same aspect ratio and increase this y's, then we can see the stable slip velocity will increase with system size until to this scale we can have a relatively stable one. But we do not go even further, so we cannot say this is the final result. Maybe at even larger systems, there's still some change. So, but anyway, it's highly scale dependent. And in terms of fluctuations, this fluctuation is decreasing with the scale, as we can expect. But then you can also find the fluctuation in other quantities, and it is also change very significantly with the domain size. And this is one side of the scale dependence. Even you have the same domain size, when you have different sampling scales, then you also have different behaviors. So this is this velocity distribution with different sampling scales in the same system, and you can find they are also different temperatures and different distributions, and they are all both not fitting the Maxwellian law. And here you can see more clearly this dependence on of granular temperature on the scale. And so then we try to understand why there is such a behavior. So then we find that if we have a bimode distribution, that is, if we include two temperatures in the same distribution, then we can give a very good presentation of this velocity distribution at different scales and also at different directions. So this is somehow a fitting correlation. So it is remain a future work to explain why these index are like this and why this form it works. So you can see still this sampling size dependence in terms of the slip velocity and also the force. So you can see the slip velocity is increased with the scale, and then this fluctuation is decreasing, and for the force, both are decreasing. So this is understandable because if you have a higher slip velocity, then they have lower drag coefficient. So this dimensionless drag will decrease. And also, we have the structure dependence of the drag in even for the static particle configurations. So we can see if you have very simple two particle configuration with different orientation angle to the fluid flow, you have different drag. And if you have this stepwise change, then with different orientation to the fluid flow, also different drag. And the interesting thing is they both have a nearly linear variation in this range. And if you have a linear concentration gradient, then you can also find this gradient distribution of the dimensionless drag. So then in the dynamic case, we can also find interesting difference. So if you have this the dynamic simulation and you get a different particle configuration in the process, so this kind of configuration with the particle cluster almost parallel to the fluid flow, it have very low drag coefficient, or you can have a very high slip velocity. And on the contrary, if you have these particles almost in a slugging form, then you have a very low slip velocity and high drag coefficient. So this variation can be very large and dynamic. So and it is increased with the system size. And so finally, we also have some statistical analysis on the distribution of this drag force in different angles and in different magnitudes compared with the gravity. So you will find the interesting thing is the most probable particle drag force is not in coincident with the vertical gravity. We measured there's almost 10 to 15 degrees bias in the sampling. So we proposed that maybe for structured drag, this drag law should, in addition to this Reynolds number and voidage, we should also consider this gradient of the concentration and also its angle to the fluid flow. So, but this is only a form. We need to find the real correlation. Yeah. And next to the last part, I will talk about the stirred tank simulation. These are very preliminary results, first given in ISCRI 25. So this is the simulation of the whole stirred tank. And you can see the circulation of the particles, and this color is the vertical velocity. And if you analyze this flow field, you can find the very significant anisotropic distribution caused by these baffles. And the turbulence here is lower than the single phase system. And of course, this conclusion is dependent on the particle size and the density we used here. And if you go further to the circulation area, then you can find that this global circulation area is enlarged when you have the particles in the system. And on the other hand, for the drag, for the local drag, then you will find the Brooke formula, which is used mostly for small particles here, is not a well prediction. So for this 1 millimeter particles, it is almost all over predicted. And for this Ruhr and Sinclair model, it have a better agreement. So this is depending on this particle diameter, and but we think the Stokes number alone is not sufficient to correct all these drag laws. So finally, I would summarize that for the drag in gas solid or the particle fluid systems, actually at different scales there may be different factors for its difference to the uniform law. So at the most small scale is the geometry at the cell, and then the fluctuation in the particle distribution or their velocities may be the main cause, and then their gradient. And at even larger scales, it's their heterogeneity, and at even larger scales, it's the global distribution. So when we talk about the drag laws, we have to understand where is the domain we are talking about. So for the moment, I think the DNS is only possible for this part, maybe still in between this part to this part. So once this DNS can go to real reactor scale, I think we can get a full understanding of how drag behaves at different scales. So these are the main conclusions. So I think the DNS is important, but it is desirable to go to large scales to understand its scale dependence. And the drag law should also be understood in different scales because of different dominant effect of fluctuation, gradient, heterogeneity, or global distributions. So with this, thank you for your attention, and thanks to our funding agencies and all these companies. Yeah, thank you.